the
This is next slide, previous.
Hi. So Todd Rimmer actually submitted this talk, and unfortunately he was unable to attend, so I'm going to be attempting to fill in. I am by no means a deep learning or machine learning expert. I feel like I've learned quite a bit since agreeing to do this talk, but my expertise is a little bit limited. A lot of you already know who I am. Todd Rimmer has been involved in this community for a long time as well. And so with that, so basically the point of all that is that artificial intelligence is no match for natural stupidity. So here we go. Obviously, I work for Intel, so we get a lot of nice little things that you can read offline if you care. I'm not going to present a lot of performance data. There's some relative performance data. But the point of this talk isn't performance. It's not. I do have data about Omnipath, obviously, because I work for Intel. But the point of the talk is really what we do and what we've worked on over the last, for some of us, 15 or 20 years, and how it's really coming of age in some of these new workloads, specifically deep learning. So generally, what is AI? We've touched on that with the keynote this morning and a couple of those talks previous. Where can Fabric help? And then a couple of real-world examples. I know I'm between you and lunch as well, but we'll see how we can go here. So we've all heard this. AI is coming up. Bill talked about how the hype is high right now, but not a lot of people are using the technology yet. But one of the greatest stories that I've heard so far is a lot of people talk about cat and dog photos, and my wife loves cat videos, and I do too. I've got cats, but one of the coolest things I've heard is actually coming from the power industry in a very ancient career of mine. There's a company that's looking at solar arrays, and what they're doing is they take pictures of their solar array, and they have an AI algorithm that will look at those solar arrays, and by looking at the individual panels and analyzing those, they can tell which panels are going bad or need maintenance. So there's a lot of real-world good applications. We heard about smart cars and things like that. Which we all know about, but there's also a lot of real applications that are kind of buried that I think are really interesting. There's kind of a sphere of artificial intelligence. Generally, artificial intelligence is where a computer has the ability to adapt and learn and process new data that it hasn't seen before. Machine learning, and I'll get into machine learning and deep learning. So we're talking a lot about deep learning. Machine learning's been around for a number of years. In fact, deep learning algorithms and theory has been around for, I think, 40 or 50 years. And it's only been recently that the amount of data available has really made it kind of a reality, and the computing power, which is kind of where we come in with our fabrics and our scalability, which we've demonstrated time and again with all of the clusters that many of us have floored. So, that didn't come out very well. Okay, well, so traditionally machine learning is you take something, let's take the image example here, and you say, well, we're trying to identify, is this a person? And we're looking for characteristics between the width of the eyes, eyebrows, a nose, some sort of general round circle being the face. And we kind of program those attributes into an algorithm. Another example, if you go to Google's page on TensorFlow, is we're trying to tell the difference between an apple and an orange. Well, an orange is orange, an apple is red normally, but some apples can be sort of orangey. And so what happens with machine learning is it's very critical that you pick the attributes that are going to be fed into your algorithm. So a decision tree, for example, you want your algorithm to very quickly say, okay, this thing's orange, so it's probably an orange, or it's red, it's probably an apple, and then you can kind of pare it down. How big is it? How heavy it is? But you have to pick all these attributes ahead of time, and if you pick them wrong, the algorithms can quickly be fooled and be wrong. So then we get into the neural nets and the deep learning, and what neural nets provide us is the ability to basically have the computer train itself, pick the attributes that it's going to be looking at, and tune those. But it can only do this with a massive amount of data. And sometimes these neural nets need to be retrained as new data comes online. So in the machine learning example, that would be, oh, well, I picked these attributes, but oh, I threw a banana in there and it said it was an apple. So now I have to go and say, well, maybe I need to say, well, I have to say, well, it's round or not. So I have to add that attribute. And that's a manual step. With deep learning and AI, we're basically asking the computer to train itself. So where can Fabrics help? A little bit of background, a little bit more background here. The different neural nets that are available are getting deeper and bigger topologies. So the one I show, the simple one here, looks very Clos-like, right? We have multiple levels, et cetera. But there's other topologies that are out there. And these are just some of the examples that we have. And a couple of the talkers have already spoken about ResNet. There's GoogleNet. There's larger layers of ResNet, 152, and I think there's one that's even bigger than that. And so that's part of the problem as well, is the neural nets, they're getting bigger, they're getting more complex, and so in order to train those, that further complicates the problem. So now we have a big data problem, which we just heard a talk on Hadoop and big data. Now we're talking about a bigger problem with the amount of computation we need. Then there's a lot of different frameworks, a brief talk on frameworks. These are basically the frameworks that people use. TensorFlow's from Google, Caffe, Microsoft has one, Torch. And what we're also finding is the frameworks and the people who develop them are recognizing these are some that I found that were actually multi-node capable. The others may be, I don't know, the data I had might have been a little bit outdated, but as you can see, a lot of the frameworks are starting to go multi-node, which again, if you've got multi-nodes, Fabrics, we need networks to connect them. So I touched on this a little bit. We've got big data, we've got bigger models, more computation, deeper neural nets, and many of the neural nets can be used for multiple different applications. So same neural net, but it needs to be retrained. Or we have additional data because we think we can get a little bit more accuracy. So the ability to either retrain your neural net or add more data to it and train it with more accuracy is increasingly important to people, which leads to the computation, the scalability that people are driving for. So over here, Google mentioned that if they can basically retrain and run their neural net in a matter of a few minutes, they can do interactive research. 1 to 4 days is tolerable, but okay. 1 to 4 weeks is like, well, if it's something really important, I might go ahead and run and do the training over that time. If it's greater than a month, we're just not even going to bother with it. It's not important enough. So what they really want to get to is the point where they can retrain the neural net and do this interactive research very quickly. So going towards multi-node training, we start with a single server. We kind of develop our neural net. We kind of run a little bit of data on it. We basically see some interesting results. We drive that into, we need more data. We're going to train this. We want to get more accuracy. Now the issue becomes, I need more compute power. So that drives us towards our clustering and scalability things that we are, in this room, experts in. So obviously the complexity is growing. We need timely retraining. And we're shifting to a cluster workload. Excuse me. What a lot of researchers have found is that the communication patterns that they're seeing amongst these multi-node neural nets as they're training look a lot like MPI jobs. And in fact, MPI collectives fit very well. So this morning, Bill presented something that looks very similar to this. And this has a little bit different communication pattern. But as we're basically doing our forward propagation, our back propagation, depending on how we're doing that, and I'll get into that into the next couple of slides, we can use different MPI collectives very efficiently. And what they're finding is the HPC fabrics that we have developed and the software stacks like libfabric and the MPI software stacks and even verbs to get data in and out has already kind of solved those problems. So they're basically leveraging that. So there's a couple of different ways to parallelize your neural net. This is, on the left, we've seen this picture a couple times. Just for an interesting tidbit, there's a common example, kind of a hello world of neural nets, if you will, where there's a huge database of handwritten numbers on a known grid. So you basically feed that into your neural net, and basically there's handwritten numbers and outputs. So like Bill mentioned, you feed this into your neural net. It says this is a bicycle. You say, no, it was a cat. And then you do backpropagation, which basically trains your net. So one way to do that, to make it parallel across multi-nodes, is basically have a model parallelism. So basically, your neural net, you kind of split it in half, or probably more levels. And as you're doing your forward propagation and back propagation, the data pattern is basically communicating amongst the nodes. And what? Wait a minute. OK, that slide didn't come across. So, OK, well, I'll try to explain what was supposed to be in those boxes. Basically, think of this picture. Take all of that neural net and put it in the top box, and take all of that neural net and put it in the bottom box. So basically, I don't know why the slides didn't come across. Apologize. So this is data parallelism. And basically, the idea is you have each node just running the neural net on its own with a subset of the data. So, hence the data parallelism. So you're not trying to basically spread the neural net out across the fabric. You're basically just kind of doing an embarrassingly parallel problem. However, when each of those neural nets want to backpropagate to adjust their weights and their biases, you need to communicate that to the other nodes so that they're all learning together from everybody else's node. Otherwise, you're not really getting that parallelism. And in data parallelism, you have this forward propagation, and then you have a period of communication, which is your back propagation. And then one more note on the two different models, a model parallelism, data parallelism. There is some research, and it was mentioned earlier, the MLSL library. They've actually found that sometimes a hybrid model works even better. So we're also, we're very rapidly, as this industry does, rapidly moving into even more research that we're finding that if we basically kind of mix or combine and do a hybrid model between those two, we can get even faster training. That further complicates your communication patterns a little bit, but that's kind of all worked out in that library. And it's actually on GitHub if anybody's interested in looking at it. OK, so I'm moving right along here. And so in conclusion, we have higher bandwidth networks. They're faster. They can get the data in and out across the nodes. We have lower latency networks. So generally, in our model parallelism, you can imagine how lower latency is more important as we're crossing the neural net and as we're trying to propagate those data values back in our back propagation, that being able to communicate very quickly is more important, whereas in data parallelism, being able to get the data out to the set of nodes and back, being able to retrain is obviously a bandwidth problem because we're trying to get a new data set in or additional data in or out of the cluster. And obviously, our scalable latency that we have in our networks is important in general. So a couple of quick examples here. What we've had, and these come from some of our users of Almond Path networks. They've basically been running some of these AI and workloads, and the results and the scalability are very promising. So, one of the things we focus on here is scalability, is how high up we can go. And they were able to scale very well up to 256 nodes with this workload. And as Bill mentioned earlier, actually break a record in how fast they were training. And this is growing. A lot of our customers, Pittsburgh Supercomputing, in fact, They actually floor a site, and the whole concept of their system that they floored was actually to bring researchers in from all around the world, and they've got multiple researchers doing deep learning on that system. So we're seeing AI on HPC growing already and already being used here. So it's kind of coming together already. And there, I'm quick. Thank you. Any questions?